What is up, everybody? How's it going? So today we're going to take a quick little detour. So instead of doing this how to scale your model book, we're going to dive a little bit deeper into JAX to get more of an intuitive feel for JAX, and then hopefully we can also go back to these problems and maybe start writing some of these out in JAX to help us solve them, make sure that we get them right in the first try. So first thing I'm going to do is I'm going to go to, I want to save these. I'm going to go to, let's go to my GitHub. So I have this repository, lipid nanoparticle encapsulation efficiency predictor. Let's click into this. So maybe you guys can go in and read on your own time, but long story short, this is a biophysics, it's like a physics-informed neural network that I coded up with the help of Claude, obviously. And it's supposed to predict the encapsulation efficiency of lipid nanoparticles. Doesn't really matter exactly what those are, but long story short, there's this open source data set called Lipid Nanoparticle Atlas. It's only got 1,092 data points, but it's enough to at least get the basic, enough data to start, something. So what I did was an XGBoost algorithm, and then I also did a physics-informed neural network. So we are going to, in this session, rewrite the neural network. But instead of using PyTorch, which is what I used before, we're going to use JAX. So let me see if they say anything here. No. So scroll up to the top here. Pin. Let's just look at basic. It says it here. No, it doesn't. So model.py, yeah, so you can see here we use PyTorch. So the goal of this session is literally just to port everything from PyTorch into JAX. And I'm going to try to run this code on my GPU instead of my Intel GPU instead of on my regular computer. But we're going to do some development with VS Code, just so that's easier, because I'm on a headless server for my GPU server. So let's move this bad boy over to the side. Or you know what, we can do what we were doing earlier. We can do this, and then let's get this bad boy over here. So first, don't save. Let's see, what can we do here? So first, I don't know if I have the project files locally on my computer. So let me check that. Let's see, projects maybe? No. This PC, local disk. Python scripts. Does not look like I have it. So what I'm going to do here is first I'm going to clone this repository here. So let's change directory. Bang, and then git init. Then let's do git clone cool. And then let's check if it worked. Yep, let's change directory into lipid. Oh wait, I don't think I need this. Lipid nanoparticle EE predictor. Cool. So we got that. Now what I want to do is make a new branch off of main. I want this to be called JAX. So let's see, I think it's just git branch, right? JAX. And then git checkout JAX. Sweet. The next thing I want to do now is open this folder. Bang. And here we are. So, I already have Docker on here. Well, in that case, I should move my website from Streamlit to something better. All right, so let's get a terminal in here. Get rid of chat. Don't need that. Make this small. Now, what do I want to do? So first, let's just open up physics informed neural network. Read everything. So pin module for. Okay, so this just explains what it is. Model. Let's see what's going on here. Predictor, physics informed neural network for lipid nanoparticle encapsulation efficiency prediction. Architecture, fully connected multi-layer perceptron with residual skip connections every 2 layers. Sigmoid output layer, 0 to 1. Oh, whoops, I hope that didn't. Oh. Fraction, not percent. Training objective, L total equals L data plus alpha times L physics, or dot L physics. L data is mean squared error unlabeled encapsulation efficiency observations, and L physics is the weighted physics residual physics.pi. Input features. So we got ionizable lipid mole fraction, NP ratio, particle size, PDI, polydispersity index, zeta, megavolts, our PEG lipid mole fraction. For those of you who aren't familiar with chemistry stuff, PEG lipids are just a type of lipid. So for lipid nanoparticles, this ratio is important for stability. And then cholesterol, again, another molecule. So basically, long story short, what a lipid nanoparticle is, just to give you some background. It's basically like this little ball here. Inside the particle are, it's a payload, so usually it's some genetics. So you can see here they have some DNA. And then on the outside, it's a lipid. So you have these phospholipids. You got this bilayer here. It's protected on the outside, and it protects the stuff on the inside. These little squiggly lines, those are the PEG lipids. So I think it's phosphoethylene glycol or something, but PEG stands for something. But long story short, these little squigglies kind of act like springs. So whenever the lipid nanoparticle might come into contact with like some enzyme or something, it forces the enzyme to stay away so it doesn't digest the lipid nanoparticle. But it's also super important for stability. And these little hexagons in here, those are cholesterol molecules. So for anyone here knows anything about biophysics and stuff, cholesterol is really important for maintaining the right amount of fluidity of the lipid layer. So lipid membranes can either be really fluid and soft, or they can be really stiff, and you really want to find a good hybrid. You want it to be liquid enough or soft enough that it can form into any shape, or it can have, the lipids can be moving around. That's important for a lot of metabolism stuff, and also for the mechanism of the lipid nanoparticle, which is the lipid nanoparticle is eventually supposed to pop so the payload can access whatever it needs to access. But also you don't want it to be too stiff, because then, the shape won't hold. It won't be able to hold into a sphere. And then also, it can't pop. Oh, but yeah, you don't want it to be too soft either, because you want it to maintain its shape, and you don't want it to be like liquid. Anyway, so, and then polydispersity index, we'll skip that. Particle size, self-explanatory. This is nitrogen to phosphorus ratio. It's also important for stability. And then ionizable lipid mole fraction. So there's like 3 or 4 different types of lipids in this membrane. There's the PEG lipids, there's cholesterol, and then there's ionizable lipids. I'm pretty sure there's one other, but anyway, our output is our prediction of encapsulation efficiency. So encapsulation efficiency is, so basically, when you're manufacturing these particles, we don't get a perfect sphere every single time. We don't always get the payload inside the sphere. So for positive encapsulation, It's where you have a sphere of the lipid nanoparticle form with a payload inside. And if you have an unstable molecule due to your chemical formula or whatever, you will have less encapsulation efficiency, because on average you're going to have less spheres out of your total like amount of lipids that you put in there, because it's not a stable equilibrium, you know. And the more stable your equilibrium, the better the more stable your chemical formula, the more actual spheres of those lipid nanoparticles you're going to have that formed properly and encapsulated a payload. So let's look into what's actually happening here with the current torch. So we're importing torch and torch neural network, typing import list. Sure, I think that's just for like linting. So class residual block neural network module, 2-layer residual block with layer norm and GELU activation. Fine, initialize self, you got a hidden dimension, it's an integer, dropout, it's a float, which equals 0.1 at first, super init, self block, neural network sequential. Okay, so you're defining all these on the hidden dimension. Self-activation, neural network, GELU. Define forward, torch sensor. Man, it's been so long since I've done this. I need reminders on what this stuff means. Okay, layer norm. Let's see what that is. It's a technique using deep learning to stabilize neural network training and accelerate conversions. Let's see. Batch norm. Let's do this. So layer norm, what does that take in? Okay. Applies layer normalization over a mini batch of inputs. This layer implements the operation as described in the paper layer normalization. Do that for later learning here. Anyway, let's go back to torch. So y equals x minus, what is e here, I wonder? Divided by the variance of x plus epsilon. Is that this dropout? No. Because layer norms on hidden dimension, yeah, I don't know what dropout is either. The mean and standard deviation are calculated over the last n dimensions, where n is the dimension of normalized shape. Oh, d dimensions, whoops. For example, if a normalized shape is 3,5, a two-dimensional shape, the mean and standard deviation are computed over the last 2 dimensions of the input. Okay. Gamma and beta are learnable affine transformation parameters of normalized shape if element-wise affine is true. The variance is calculated via a biased estimator, equivalent to torch variance. Unlike batch normalization and instance normalization, which applies scalar scale and bias for each entire channel / pane with the affine option, layer normalization applies per element scale and bias with element-wise affine. This layer uses statistics computed from input data in both training and evaluation models. Gotcha. Okay. So we've got a residual block here. Let's see. Let's just get a basic overview of everything and then start replacing stuff. Define forward, torch tensor, self-activation. Yeah, it makes sense. Okay, then we've got our encapsulation predictor class. Let's see. I'm just going to go through all the classes first and then we'll read what they actually are. Oh, that's it. Okay. Physics informed neural network for linear lipid nanoparticle encapsulation efficiency. It's a layer residual block. Arguments and features, number of input chemical features, hidden dimension, width of hidden layers, and residual, number of residual blocks, dropout, probability, model. Okay. Random number, EE equals model of X. Gotcha. And we probably run that a bunch of times, huh? Okay. So we're going to input projection, self.input.projection equals neural network.sequential. Cool, you're on those. Digital trunk. output head predicts encapsulation efficiency. Self output head equals neural network sequential forward. Feature tensor of shape B and the number of features. Turns encapsulation efficiency. Predicted encapsulation efficiency, shape, and values. Build model. Okay. Let's look at the next thing. Physics. So this is the physics that we need in order to work it into our weighting, our loss function. Delta G mixing dx, residual, monotonicity, residual thermodynamic mixing, residual boundary size, total physics loss. Cool. Pre-process. Okay, so one thing about this data set is that our zeta potential, which is like another like electrochemistry thing, it was missing from so many rows that I decided to remove it first for one of them. And so I tried both with zeta and without zeta. If I remember correctly, we predicted better without zeta. Let's see. Results. What does it say right here? Maybe if I go into the pin module, I'll say more about that. So why only 93 rows? So this is the bottleneck right here, is the zeta millivolts. So the thing I really need to do is increase my amount of data. That's the big thing. Well, first we're going to build the JAX engine, then we're going to improve the data. So future improvement, dropping zeta. Gotcha. I think I might have already done that though. As you can tell, I kind of sped through this, was a little messy. All right, let's see here. Index maps used by physics residuals. Okay. So we got indexing, parse molar ratio. So basically, how easy is it for me to show y'all what this looks like? I wonder if I can pull this up in Excel real quick. But anyway, so this is kind of what the data set looks like. Yeah, it's better if I open up an Excel, huh? Do I even have Excel? Maybe it will look good if I open it up in GitHub. Right? No. Oh, and it's got problems with that. Let's see what I can do here. Edit with Notepad++. No. So, I mean, this is a little better, I guess. But if you look at this, the big thing is we've got this, so we've got our molar ratio, which looks something like this. So we need to parse these values here. Another big thing that we need to parse is, where are the smiles? So I think it just says the title of the column is just like PEG lipid original or something, or ionizable lipid. But anyway, you can see all these values here, which are just like long strings of like C's and O's. So this is what's called a smile. So it basically says, it's like a language to describe molecules. So this is like a chain of carbons. some oxygens. Here's, I think that's called a ketone group, and more carbons and oxygens. And what we can do is, if I go back to, no, not in model, it's in pre-process. So parse molar ratio, clean numeric, parse encapsulation efficiency, let process. Oh, is there no smiles thing here? Oh, never mind. Well, I guess that I don't even parse the smiles. Well, whatever. I guess the really important physical characteristics are the actual numbers rather than the smiles themselves. So I think I just have to parse lipid molar ratio. I don't think we use helper lipid. Then we want to look at particle size. Yeah, so I think this number is like this, like 19, 91, etc. Anyway. Alright, let's keep looking through this. So this pre-process thing is pretty self-explanatory. I don't think I'm going to have to change anything to port this over to jax. Maybe we can use JNP instead of NumPy. I mean, why not? Let's try that now. So yeah, let's just edit right in place because we're using Git. So why the hell not? jax.numpy as JNP, and then let's go to NP. Let's replace almost everything as JNP. So first thing, nope. Okay, don't want to replace that. Don't want to replace that. We already did that. No, it's good. So we want this to be JNP, and JNP, 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 skip, skip, JNP, 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 JNP. Okay. And this probably has a lot of NumPy too, right? No, it doesn't. So we'll postpone importing or switching from Torch to jax for now. Now I just want to verify that the JNP worked here. So I kind of just want to run this. I should be able to run it on my CPU fine, right? Probably. So here's what I want to do though. I just want to start running it on my other computer at home, my nice computer. So I'm going to try to SSH into that. Uh-oh. Alright, cool. And then let's make a new directory. Or no, we can just clone right from here, right? Yeah. Might as well just clone. Or no, let's do this. Make dir, let's make it lipid nanoparticle EE predictor. Let's change directory into that. actually, let me see something. Do I have a general scripts or something? No, I don't. So let's just go back into that. All right, and then git init. And let's git clone this bad boy again. All right, done. Check everything. Oh, well, let's change directories into that again. Awesome. And then let's see if everything's in there. It looks like it is. Sweet. So let's git checkout. Oh, before I do any of this, I need to push these changes. All right, well, in that case, let's do git commit bang changed numpy to jax.numpy and started new jax branch. Oh shoot, I need to add everything first also. Okay, so git config global bang. Let's also do all right, hopefully that worked. All right, git add. I think I only changed preprocess, right? I mean, it says that I changed physics too, but whatever. All right, git add pin, then preprocess.py, and then git commit. Let's try to copy this. Nothing to commit. What? I mean, nothing to commit. Oh, okay. There we go. All right, one change. And let's git push. I need to set my remote origin, huh? Forget how to do that. How to set remote origin git. Git remote add origin bang. Oh, what? Git remote. Oh, whoops. So why did git push not work then? Oh, okay. Git push set upstream origin jax. Oh Lord. Let's try this one more time. Let's see. Let's go back here. Did the changes work? There we go. Let's go, baby. All right, get jax. Changed 1 minute ago. Heck yeah. Okay. The next thing. What is the next thing I wanted to do? Oh yeah, just test that it works. So we SSH'd into it. First, let's get pool. Already up to date. Perfect. Is it really? Do branch, I guess. Git checkout jax. ls pin. Well, actually, I don't think I really need to do that. Anyway, let's see. How do I run this again? Let's see the physics informed neural network instead. Should add this to the main README as well. Project root. Let's do this. No module named torch. Oh, I need to pip install the dependencies, huh? Source bin venv. How do you make a venv in Linux again? Let's see. Okay, cool. So we're on the base VM, but I don't want to be on that. Oh, wait. Let's do conda create name, nanoparticle, venv. Yes. Okay. Then conda activate lnp env. Cool. And then let's pip install everything. Brother. Let's do this. Actually, I also, maybe I can do uv pip install our requirements.txt because I'm pretty sure I have uv installed already. Yeah. There we go, baby. All right, well, let's see. Let's just make this bigger. Yeah, I don't know what's wrong here, so I'm going to just put this into Gemini. Let's do this one instead. Oh, but I still need to delete the first one, right? Let's do that. Oh, bruh. How do I deactivate again? Conda deactivate. Alright, next. Remove it. I hope there's no problem with Conda where that didn't work, but oh, whoops. Alright. Let's try this. Oh. Okay, and then UV pip install. Let's see if it works this time. No solution. I wonder how I got it to work on the previous thing, but okay. Well, I'm gonna go back to work. My lunch hour is over, but we're gonna pick up where we left off here, fix this error, and then hopefully test if jax.numpy successfully replaced numpy in this thing. So we're gonna take a quick break, but I will be back soon. So catch y'all then. All right, we're back. So when we left off, we were having trouble with our packages. So let's SSH back into here. And I think what I'm going to do is build a version with Python 3.9 and then get rid of Streamlit because we don't need that right now. And I guess we can figure that whole situation out later. I'm curious how this used to work though. I don't know why it won't work now. Alright, we're in. So everything's still there, cool. Cool, EE, predictor. Let's run that again. And then let's go into our requirements.txt file. Oops. Let's get rid of, oh, maybe I already did it. So we got Jax in here now. I don't see Streamlit. Oh, the only thing that we need to do now is just rebuild a new conda env with Python 3.9, I think. So let's talk this guy to the side. So I thought I did that already. So let's do conda deactivate, and then conda activate lnp vn. Let's try to do this one more time. UV pip install our environments.txt. Okay, so local system environment bound directly to 3.9. So I guess I need to actually write that down explicitly. Oh, let me scroll down further than that. No, whatever. All right, conda deactivate. Let's do conda Or, oh, that's why. So UVVM. Let's do that. Bang. I'm gonna replace it. Yes. Okay. Let's do this bad boy. Bang. And then let's do this again. It should work this time. We don't have Streamlit. Let's find out. One thing about UV that I really like is this little like animation here. It looks very like early 2000s movie hacker-esque, you know? It's like I'm the Matrix downloading all this knowledge. So I wonder also, I wonder if I even need SHAP if I'm going to be doing a physics-informed neural network. I think SHAP was mostly for XGBoost. Let's go back here and see. I'm pretty sure SHAP was for just XGBoost, but I guess we'll find out as we dive deeper into it. Okay, architecture input goes into linear, layer norm, JELU, skip connected, two-layer perceptron. This looks very similar to the residual block. Interesting. All right. Yes, I don't think this is relevant because this seems like it's serving the XGBoost model. Man, these packages are taking a while. So let's see in here. What does the train pin call? Oh no. Oh shoot. There we go. Scroll down this bad boy. Legacy pin training entry point. It's legacy. So it uses a random trot, train, split, mystic. Bruh, it's hidden. Whatever. Data leakage. I use pin train pi directly, yeah. So unfortunately, I need to update that in the README. Well, I don't think I should bother with this. Or should I? I mean, this doesn't look like it does nearly the same. Oh, train.py. I didn't even edit this one for the NumPy stuff yet, so. Should probably do that, huh? Well, let's do it now. Alright, let's do jax.numpy np. Let's keep going. Oh, whoops, I need to do it as JNP, right? Jax.numpy is JNP. Let's go back. Oh. JNP, 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 JNP. Yeah, sure. Oh, whoops. Next one. Bang, 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 bang. Cool. So I think all of that should be good now. File, save just in case. Let's go back to this regular PowerShell here. Let's do git add pin train dot py and git commit changed numpy to jax.numpy and pin/train.py. Cool, and then git push. Sweet. Now this seems like it's done. Let's git pull. All right, looks right. And let's run it. So I think all we have to do is just run train.py. Let's look in here again just to make sure in this readme. So this does not say how to do it. Oh, it does. Okay. Hope this is right. Oh my lord. Let's get rid of this comment. So Python pin.train 300 flex. See what happens. Traceback. Cannot import name, load and process the cruise from pin process. Why not? Is Jax even working? I mean, let's find out, I guess. So I need to remind myself how to run Python in terminal inline. Python C followed by code wrapped in quotes. Okay. Let's do Python C import jax. Or let's do try import jax exception print didn't work. Why did that not work? Is it because, okay, I mean, you can try that, I guess. Python EOF, and say import if import, or let's say try import. How do I do the white space? Tab's not working. Okay, 4 regular spaces, 1, 2, 3, 4. Try import jax exception 1, 2, 3, 4. Do I need to say Python 3? No. Exception. Print. Nah, homie. valid syntax. Right, how do you do that? How do you do that again? I mean, if I just say Python import jax, it'll probably give an error if it doesn't work, right? Okay, well, it looks like it works. Let's try this. Python uf import jax. Okay, now let's try this. Oh shoot. Python uf try for port jax 64 print success exception as check module not found error. Okay, sure. Do that. For print homie uf success. Okay, so is the jax.numpy not working? Shoot, I guess I have to redo the whole thing, huh? Oh no, maybe not. Import jax.jmp as jax.numpy as jmp. Okay, well, whatever. Alright, so it's something else that's wrong. So the problem is this code was working fine before I started messing around with it now, so I don't know why it's not working. So is that actually, no, load and preprocess is right here. Maybe it needs to be in the init.py. Maybe I need to change directory and set the pin first. No. Pin load and preprocess. Why is that not working? It definitely exists. What? Oh, with groups? Alright, now we gotta audit the entire freaking thing. Oh, gosh darn it. Alright, where does it say load and preprocess with groups? To the top. It's importing both preprocess and non-preprocess with groups. But I really have to figure out where the load and preprocess with groups got dropped. Well, unfortunately, I'm going to have to resort to Claude for this. Oh my lord. I don't even have Claude installed on this thing. Alright, let's see what he says here. Alright, it was deleted. 0, scratch, match, features, mismatch, imports, list. Oh, whoops. Yes. Go do it, my boy. And after this, we'll try to stay off AI help as much as possible. Just trying to use it for the plumbing. A little boring stuff. Oh shit, maybe it's changing way more than I wanted. Uh-oh. I accidentally clicked. Alright, well, we can dive deep into exactly what it did later. For now, let's commit. Actually, yeah, commit and push. Just have it do it so we don't have to get out of Claude. Alright, let's see here. Bash, get add, get commit. Okay. Man, Claude's commit messages are always super long. See, the problem is when you click, it just does it. Because I'm used to Copilot at work where you have to click every single time before you can hit a button for some reason. Alright. Let's try this again. Git pull. Sweet. Now, let's run. Please, 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 please. Oh, Lord. There's no attribute random. Oh. Oh, I have to redo all the random seeding stuff. Oh, Lord. It's gonna take a little while, probably. Well, I'm gonna take a little break, and then we're gonna come back, and we're gonna fix all the random number generation with jax.numpy. Alright, catch you in a little bit. Never made it as a wise man. I couldn't cut we are back, everybody. We are back. This time, we are going to be continuing the porting of our NumPy to Jax. Go back to Jax 101. Oh, whoops. What we want to do now, like I said earlier, is I'm like you, I'm sorry. I'm sorry. Alright, so we want to look at pseudo-random numbers. So let's go back. Let's see, where did it say in terminal we had an issue specifically? Jax.numpy has no attribute random. What? Well, I'm just going to go through all of the Python code in this pin module, and I'm going to see how we can port them to Jax. Better lighting. All right, let's see. So Jax, I'm pretty sure not a number should work. Let's go through every single one. Cool. jmp.clip. I assume that's fine. There's no attribute random. Okay, that should be fine. That should be fine. Float 32. Yep. Bang bang. Cool. Arrays. Yeah. Okay, so it looks like pre-process should be fine. Let's see, maybe in model. There's nothing in model. Okay, then train. So first, good. An array. Zeros, they have that. Unique should have that. Okay, random seed. Let's read this function just to know. Okay, so this is group K fold. All right, jax.random, pseudo random number generation. NumPy.random.seed. Yes, this is exactly what that is. Repeated calls to NumPy stateful pseudo random number generators. Mutate the global state. Stream pseudo random numbers. Don't care about that. Okay. That's what we do. So we just have a seed, and where do we call that seed? So what's this saying? Okay, so we get a random seed. So random permutation. Is that all it's used for? I'm wondering if we fix the seed, if that fixes everything else, or we have to completely rewrite this. Okay, let's see here. Reproducible, parallelizable, vectorizable. Yep. Isn't that the same thing as sequential they're just talking about here? It's two scalars sample from uniform distribution. Give me 1 second, my friend's calling. Alright, cool. The output of this code can only satisfy requirement number 1 if we assume a predictable order of execution. This evaluates code in the order defined in the Python interpreter. And jax, yeah, because the JIT compiler wants to reorder stuff. Gotcha. Explicit random state. Yeah, key. Yeah, I remember this now. Jax import random. This should be, is there a J and P random thing? I thought I saw that earlier. So from jax import random, key equals random.key. Okay. Okay, so keys and array is a special data type corresponding to a particular PRNG implementation being used. Implementation, each key is backed by a pair of U32 values. Effectively a stand-in for NumPy's hidden state object. We pass it explicitly. Consume the key but do not modify it. Feeding the same key object to a random function will always result in the same. Yep, okay. Using the same key APIs can result in correlated outputs, which is generally undesirable. Okay. Never use keys using the same state. Cause sadness. Sadness. Okay. Jax uses a modern 3-fry counter-based PNG splittable. That is, its design allows for us to fork the PNG state into new PNGs. To generate different independent samples, you must split the key explicitly before passing to a random function. Man, what is going on here? Oh, okay. Alright. Alright, let's see this example for I in range 3, new key, subkey equals random split key. I don't think I need a subkey or anything. Right? So I wonder how exactly is this generating independent samples? Okay, so let's remind ourselves what run group kfold does. Cross-validation of paper DOI groups trains a fresh model per fold with a per fold scalar to prevent leakage. Returns aggregate and per fold metrics in eSpace. Okay, so number of features, group K fold equals group K fold, specific arguments, dot unfolds, F predictions, length Y type. Okay, metrics and groups equals groups, prints, cool. For fold, train IDX, val IDX, train and value index, and enumerate. Split X raw, Y and groups. Reproducible per fold seeding. So this is where we need to. Yeah, so this says it wants it to be reproducible too, right? So I think, so we are creating a new key each time, each different fold, I think, but I would assume, do you need to destroy your key each time? You must split the key explicitly before passing it to a random function. I don't know if we do independent samples, but we can look at that later. Clicking del here is not required. We do is emphasize the key should not be reused once. Okay. Yeah, we're not going to reuse it. So maybe I have to say jax import random. Let's just try that at the top and see what happens. So do from jax import random. Scroll back. Let's do, I think we just do random.seed, right? All right. So we've got our seed, yeah. Bang. Anything else? Just allows sampling vectors of numbers. However, jax does not provide a sequential equivalence guarantee. Sure. All right, let's see how it differs. So NumPy, jax's random module also allows sampling of vectors, does not provide a sequential equivalence guarantee because doing this with inferior vectorization. Example below, sampling 3 values at a normal distribution individually. I don't think this matters for us though. Let's see. All right, so where was I? So random.seed. Let's see where else we use that random seed. So for this, oh, whoops. Where is the jax random seed even used? Train loader, validate loader, model optimizer, okay, scheduler. Is it using a mean squared error? No, there's no way. I might just try to just see if this notation works, and maybe we can dig into the plumbing a little bit more just after we see it, whether it works or not. I mean, I guess let's try it here. Let's see what happens. Can't remember. Am I running it on the node? So that means I installed jax in the node, right? Maybe I'm running on that node's CPU. That's what I would guess. We can move on to the GPU after that. Anyway, let's log back in. Cool. Let's try this again, see what happens. No module named pin. It's for this reason. Alright, never mind. That's just right from scratch. Alright, what is it called again? Okay, that's what it's called. Lipid, nanoparticle, EE, predictor. And then do that again. And then we should just be able to run it now. All right. Let's see. No module named jax. I thought I installed that already. Didn't I install the requirements? Oh, do I need to do it every time? Might. pip install. Oh, also I probably need to activate the virtual environment. That is probably what it is. And then conda activate lnp and is that how it was spelled, or was it the hyphen? Maybe it was a hyphen. What? Okay, what's it called? Oh, it's not in here. lnp venv. Oh, what was I writing? Conda activates lnp venv. There we go. All right, let's try it now. Python's not found, really. No module named jax. All right, let's see if I need to UV pip install that again. Build failures. Man, do I need to specify? Oh yeah, I need to specify every single time. That is so annoying. Okay, let's conda activate lnp venv. And what do I say? Like Python 3-3.9.0. Forget how exactly did I do that last time. All right, I gotta put this into an LLM again. What was wrong? All right, let's do it again. Conda deactivate. And I guess we're gonna make a brand new one. All right, and then let's do this. Oh, it's a UV venv. Man, I keep forgetting about that. Keep assuming it's conda. Well, whatever. We made a new one. All right. Now we did this exact same issue last time. No module named jax, of course. Oh, because I made a new thing. I need to UV pip install everything again. All right. Let's do it now. jax.numpy has no attribute random. All right, so maybe there's another thing that does that. Maybe I just never saved my changes. Let's try if I save my changes. Does that do anything? Nope. All right, let's see. Not seeing anything that needs random stuff. There's nothing here that's random. see. Does this mention specific stuff? It's in train.py. Torch manual seed. Is it not running the right version or something? I need to like commit it first. Let's commit it first, or ask Claude. No. Why ask Claude? Git commit. Oh, whoops. Git add pin / train.py. Git commit. Changed random seed from numpy to jax random library. No changes added. What? I have to add everything? Okay. Maybe now it'll let me run it. Bruh. Well, let's go to Claude. Let's see what Claude says. And later, I might want to move to using OpenRouter's Fusion model. Seemed like that was really powerful. It should also be a lot cheaper. OpenRouter models. Let's see. That's the new one that Japan just released, huh? Okay. Can they just give me like the best? I want to see what are the best. Sure. Fable 5. Yeah, it's not available anymore though. What happened to the fusion thing that they were talking about? Well, anyway, let's look at this bad boy. No, we're not using NumPy. Okay, let's see. So what do you mean jax has no seeds? Oh yeah, it uses keys, huh? So we gotta really rewrite this bad boy. So I think it's only used for permutation. All right, let's go random. Random.seed. Yeah, we don't want that. Just comment this out for now. Comment this out. Random 80-20 split. So let's see, what can we do here? Maybe it's in the API. I should search for it instead. Let's see. jax.random.permutation. Does that exist? So it uses a key, so let's make a key. Oh, freak. What did I just do? I don't know what that was. I must have mistyped something. Okay. Let's do key almost equals random. What is it? Is it random.key? Might be. Let's go back. Random.key, yeah. Key of, and then let's just say that. And then hopefully this works. Oh yeah, let's do that. Bruh. Alright, it's used anywhere else. I don't understand why we need a random seed here. For these? I don't think so. I mean, Obviously, it's got to be in there somewhere. All right, well, let's keep going. See what else. I think that's it. Let's see. Oh, that I didn't save it. Save. No. Line 254. Device. Line 342. Yes, it's calling main. And that's going back to line 254. Torch seed. And then line 46. Parse arguments. This should not have anything to do with that, right? Line 87. Line 342, already saw that. Line 255. Yeah, I don't get what's wrong exactly. No. Let's see what Cloud's got me for me this time. And in the meantime, let's go back to Open Router. Let's look up Open Router Fusion. Okay. That actually sounds really expensive. Where is this? Line 255? Uses torch manual seed. jmp.random. Well, let's try this, I guess. Find.type name by cache, except, okay, removing by cache. No, then running the thing again. Nope. Oh, shoot. Oh, man. Gosh. Keep mistyping stuff. Random seed, random permutation, in pin. Huh. So it does defer. Oh, Lord. It's because I'm changing in the freaking... It's because I'm changing in the wrong place. I need to git commit and then... Alright. Whoops. Git add pin train.py git commit changed np.random to jax pseudo random number generation scheme. Gotcha. Okay, and then it gets push. Oops. Okay, that's weird. Let's get pool. So how do I stash this here? Oops. All right, let's see what it says there. All right, let's see what this says. All right, cool. Let's do that. So reset hard. That's what I need to do. All right, perfect. So please work, please. Man, oh, is it because this is probably because of the immutability thing. Now, let's verify that. Get a different error now. This due to the immutability issue now. I'm guessing the answer will be yes. JP.clip can't accept the pandas used directly, only NumPy or jax arrays. Show the underlying values before passing to jax. The line and preprocessing these values. Okay, that makes sense. Just accept that. Parse molar ratio returns JMP.not a number. Parsing fails. Let's find your jax arrays. Penalty frame. Oh, come on, bro. Oh, it was in the pre-processed one this time. Yeah, that's fine. I'll let you give me the co-author commit thing. All right, let's see. Does this work? Git pull. Bang. Run this again. So it looks like it's kind of working. Well, in that case, while it runs on my CPU, which will take a little bit of time, let's see. First of all, I just want to see what's wrong here. Why is it throwing an error and then still working? It's weird. Yeah, so when I return, I want to take a quick break, go watch a World Cup game. When I return, we're going to troubleshoot what that error exactly means. Oh, this is done. When I return, we're going to troubleshoot what exactly that means, and then we're going to port more stuff probably from Torch into NumPy, into jax. So stay tuned for that, and I'll be back in a couple hours.